Hello everyone, welcome to the course on Artificial Intelligence in Industrial and Management Engineering. In the last lecture, we were talking about genetic algorithms and we have already introduced what are the differences between heuristics, meta-heuristics, and why do we need, after introducing, what are the exact solutions and how we can find that. So, let us now continue by understanding what are the principles behind the evolution of genetic algorithms. So, genetic algorithm is based on Darwinian evolution theories. So, there are 4 basic principles. So, these principles are principle of variation, principle of inheritance, principle of selection, and finally crossover and mutation. So, the principle of variation states that the individuals differs in trait. Okay. Now, inheritance states that some traits from the individuals get consistently passed from parents to children, right. The principle of selection states that only the fitter individuals survive. And finally, these are 2 operations like crossover and mutation, and their main role is to introduce diversity, that is the uniqueness in each individual, right. So, this is the uniqueness of individuals. So, summarizing all these 4 points, we can write that evolution maintains a population that vary from each other. Okay. So, if a particular individual is better adapted to the surroundings, then the chances of survival increases, right. And your crossover maintains diversity. So, crossover maintains diversity, but what does this mutation do? Mutation helps in maintaining this diversity by introducing random variations. Right. So, based on these basic Darwinian principles, we will try to mathematically formulate particular problem by utilizing these principles, so that once we start searching for solutions, we will utilize all the individual principles to keep the agent that we are trying to develop to keep on looking for a better solution, right. And if the solution is not good, then we can remove that from the solution space as an individual. So, let us now understand what is the analogy of genetic algorithm with evolution, that is with the Darwinian evolution. So, the task of genetic algorithm is find an optimal solution to the problem, right? Now, how can we utilize the Darwinian evolution? So, there is population in Darwinian principles, and each population is containing multiple individuals, right? So, we will try to create a set of candidate solutions for our problem. So, these candidate solutions become the individuals in your Darwinian evolution, right? So, these individuals are possible solution. Okay. Then we will create a fitness function, and it is the actual measure of the solution quality. So, the evolution principle states that if a particular individual is fitter, then the probability of surviving that particular individual increases. Similarly, here our candidate solution is an individual. So, if the fitness of that particular solution is in line with our objective functions, then the candidate solution will stay for more time in the system, right. So, now this is an iterative process. First, we will select some of the individuals from the population. Then we will conduct a crossover, that is, we will change some of the characteristics of that particular individual and create new offsprings or new children, right. Then we will do mutation, that is, we will allow random variations in those offsprings or children, and then we will get the next generation of individuals, and we will find what are the fitness values of those next generations that we have evolved, right. And this randomness which we are infusing at mutations or at crossovers, these are the things that will allow our agent to find the better solutions in the solution space very quickly. Now, how can we portray our possible solutions into mathematical form for a particular problem, right. So, let us now understand how can we represent these solutions by utilizing genotype representations. So, these are the collections of genes that are grouped into chromosomes. So, these are the terms from the biology that are into Darwinian evolution theories, right. So, chromosome is a solution encoding for our problems, right. And this is composed of genes. So, each chromosome of the child this contains a mixture of genes from parents. So, we are generating new chromosomes after the crossover stage, right. So, at crossover we require two different chromosomes that are individuals in our solution space, and then we will do the crossover to create the new child which will contain a mixture of these genes, right. So, This is how we represent a single genotype. Now let us talk about the population of solutions. So a population is a multiple candidate solution where each solution is a chromosome, and these chromosomes are evolved over generations. Now our population should maintain or diversity in the search space. So why do we require multiple candidate solutions? That is, why do we need population? So why do we need population? Because there are two reasons: exploration and parallelism. Okay, so we need multiple solutions to reduce the possibility of getting stuck in local optima. Okay, and parallelism requires because we need quick convergence. And how we can do this? We can use different possible solution to evolve simultaneously, and once they get evolved, we will again try to find the fitness values, right? So now what is this fitness function? So fitness function evaluates the quality of the candidate solution. It defines the objective of the problem, right? So when we were trying to define the objective function in our facility layout problem, we were actually defining the fitness function, right? So if the values of the fitness function is higher, that is higher values of fitness, chances of survivability increases. Okay, so this function helps GA to find and move towards better solution. Now let us talk about an example. So let's say we need to arrange machines to minimize the material handling cost. Okay. So, fitness can be defined as material handling cost. Now, usually we use genetic algorithms to maximize our objective functions, but here we are trying to minimize the material handling cost. So, to formulate this problem into genetic algorithm, we will use a minus before the actual material handling cost. So, it will invert the fitness function, right. So, negative value will maximize the fitness value, and overall it will minimize because we have used minus. So, now let us talk about selection mechanisms. We have talked about the population, individuals and fitness. Now, we will be talking about selection and then other operations like crossover, mutation and next gen, and what happens when we do the next iterations, right. So, let us now understand how we select out of all those individuals in a single population. So, this selection mechanism chooses the individuals for reproduction. Now, what is the fundamental decision behind choosing the individuals for this reproduction operation? So, it is based on the probability of getting chosen as an individual is proportional to the fitness of the candidate solution. So, if there are fitter solutions, then by utilizing these fitter solutions we will have more offsprings, and other less fitter solutions will get rejected, right. So, now also sometimes what happens is, even though a particular candidate solution is less fit, still the algorithms will keep that in the solution space, because we also need to maintain the diversity in the candidate solutions, so that when we are trying to perform the search in the solution space in the next iteration or the next generation, then these diverse candidate solutions will help to find a possibly a better solution, right. So, one of the selection mechanism is roulette wheel. So, let us say we have 4 candidate solutions, and their fitness values are solution fitness. So, there are A, B, C and D solutions, and their fitness values 40, 30, 20 and 10, right. So, the total fitness of all these solutions is 100, right. So, the selection probability is individual's fitness divided by total fitness. Okay. So, probability of selection for A is 0.4, 0.3 for B, 0.2 for C and 0.1 for D, right. Now roulette wheel looks something like this, and they get divided into different sections. Okay. So we usually spin this roulette wheel and the probabilities are already assigned. So we spin the wheel. Now these sections are denoted by the values of probability. So a higher probable solution will utilize more space in the roulette wheel as a section, right. So let's say A is this, then B, then C, then D. So after spinning, the chances of getting the solution with higher probability is higher in choosing during selection phase. But weaker solutions also have a chance to get selected. So that is how the diversity in the solution space remains intact, right. Now we have selected, let's say, few of the solutions. Now we need to do is crossover, that is recombination. So this step combines genes from two parents, and after combining, this creates new offsprings, and these are also the candidate solutions, valid candidate solutions. So why we are doing this crossover step is this promotes exploration and recombination. So let's say we have two binary strings 0 1 0 1 1 1 0 1 0, okay, and another string as 0 1 1 1 1 0 0 1 0, okay. So what we can do is in this simple crossover operation, what we can do is, let's say we take these values and the last four values from the second solution, and we just swap these values into the to create two new candidate solutions. So this will become so we have only swapped these last 4 bits from both the chromosomes and created two new candidate solutions, right, and these new candidate solutions will further get the chances of mutations, right. Now let us understand what is a mutation. So the purpose is to refresh the population. With refresh, what we mean is, let's say in this example which we are discussing in the crossover section. So here whatever you have as a candidate solution, you are just swapping it with the different solutions, but the bits in your chromosomes are not yet created out of randomness, right? They are based on your simple heuristics that you are implementing at this stage, that is, take the last 4 digits and swap it with other one. So this heuristic will keep on doing the same thing for all the candidate solutions at all generations, but we need to implement the randomness as well in our population. So to introduce that randomness, mutation operator will create and refresh the complete population. So this introduces new patterns in chromosomes. Okay, and these new patterns will allow us to search in new uncharted solution space effectively. So summarizing this mutation operator, this randomly alters the candidate solution and by altering this we can utilize the uncharted solution space, and also we prevents premature convergence. So this can be like, let's say your solution, your candidate solution after creating the crossover is 0 1 0 1 1 0 0 1 0. So let us just change this bit into the 1. So after mutation it can become 0 1 0 1 1 0 0 1 1, right? So this is a new candidate solution which was not available in your population space, right? So now let us stop here and we will continue understanding the different kinds of foundational concepts of genetic algorithms in the next class. Thank you.